disk. So on whatever day it was, Monday, we were talking about using truth tables to determine whether an argument was valid or invalid. And the procedure we used was that you take your original argument and you represent the statements by letters, and then you write the statements symbolically, as we've done many times. And then you form the entire logic statement such that the premises are connected with an AND statement, and then the premises are connected to the conclusion by an if-then statement. And then you just fill it out like a normal truth table. And if you get to the end and you get all trues in the final operation, which is usually the if-then statement connecting, well, it always is, it's the if-then statement connecting the premises with the conclusion. If you get all trues, then that means it's a logical argument. And we did an example. This one started off without having any words. We started with symbolic logic. It would be something if statement P, then statement Q, if statement Q, then statement P, and then our conclusion was P and Q. So we were able to create this logic statement that consisted of the two premises with an AND connecting them. This was our conclusion. This was our operation connecting the two. We did the table, and we ended up with this result. And the final column was true, 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 false. It wasn't all trues, and therefore this argument represented by this symbolic logic is not a valid argument. Okay, so that's where we were. Now there are a number of different arguments that are used so often they give them special names. These are in your book. You don't need to memorize them, but we're just going to go through them. And we've already actually done one of these. I think the first example that we used, this one with Julie Nem. So it was if P then Q, the second premise was P, the conclusion was Q, and we found out that the final result was all trues, and therefore is a valid argument. And that has a special name. And I guess it has to do with lawyers, because that's what lawyers try to do. They try to convince the jury, if this happened and this happened, then the guy's guilty or then the guy's innocent. And so this is the argument. It's called the law of detachment, and it has some Greek name or Latin name, modus ponens. Probably did that wrong. It's a valid argument, and if we've already done it, so we know how it works out. Fallacy of, well, actually this is an example of an invalid argument, which is the fallacy of the converse. So people try to use this argument, but it's not. Sometimes it's true and sometimes it's not true, so it's not a valid argument all the time. I think we might come back and do this one. I'm just going to go through the list. There's also the fallacy of the inverse. And if you remember back when we talked about converse, inverse, and contrapositive, we said that the original argument, the conditional statement, and the contrapositive were always equivalent to each other, but the converse and the inverse were not always equivalent to each other. This is kind of the same thing, is you can use this argument of the converse or the argument of the inverse, or the fallacy of the inverse. Both of those end up not having trues in the final column, all trues in the final column. Oh, yeah, so what I was using this for was just to write out the logic expression that we would apply in the truth table. We're not going to go through the whole truth table, but if we ended up with these as being our arguments, the logic argument, let me just make this a little taller, would be if P, then Q, we connect that to the second premise with an and then we would use an if-then statement or an if-then symbol to show the conclusion. So that would be the logic statement that we would use. Now for the second, this one that's a fallacy, if we applied did a logic table or a truth table for this expression, which would be if P then Q and Q, so that's our premises, and then our conclusion is P. And if we applied truth tables to this logic, we'd end up with not all truths. Here's another one, just again, show you how we would fill it out. So we do if P, then Q, and not P, not Q. So again, we could make a truth table for that. We'd find out that you don't get all truths at the end. Now this is just as I mentioned, the contrapositive is always equivalent to the original conditional statement, and therefore using the law of contrapositives, it's also called indirect reasoning. It has some Latin name as well because it's used a lot. So it's if P then Q, not Q, therefore not P. So again, what we would do is we take the first premise, we connect it to the second premise with an and then we connect that to the conclusion. And if you do the truth table for this logic statement, you'd end up with all truths, and therefore it's a valid argument. Let's do one of these just to review how that works. So we've represented the logic statement or the argument in symbolic logic. We've written the expression. We now need to make a truth table. And let's see, we're going to need five rows because we have P and Q. And we need one column for P, one column for Q, and then we need 1, 2, 3, 4, 5, 6, 7. So we need nine columns and 5 rows for our truth table. And the expression is below, but I'm going to write it again so we can put this on one page. Okay. So P, Q, our logic expression. So since we have two statements involved in this whole long thing, we just have 4 rows to get all the different combinations of trues and falses. And then we just copy them down, or we copy the complement, or what do we call that thing? The negation, I guess. Yeah, the negation. That's the right terminology. So now I've got the negation of Q, so I need to do false, true, false, true, and the negation of P is false, false, true, true. Okay, so we go to the innermost parenthesis, which is this one, so we'll do that first. And this is the if-then statement. An if-then statement is only false if the first one is true and the second one is false. So that one's false and the rest are true. Next, we do what's inside the brackets here, and so we'll compare we'll take the result of what was in the parentheses and we'll compare it with what's on the other side. So we're going to compare those 2 columns, and we're using an AND statement. So the rules for the AND statement are that it's only true if they're both true. So we go, so the only one that's true is this one down here. That's the only one that has true for both cases. All the other ones have at least one false. So this column represents everything on the left-hand side. So we're going to compare that with what's on the right-hand side. And we'll put the results in the space that's left. So if I take my fingers and I put them on there, and what I'm looking for is, again, it's the if-then statement, which says it's only false if the first one is true, first statement is true, and the second statement is false. So I put my fingers up here, and I look to see if I've got any trues and then falses, which I don't. So the result of comparing these two columns is all trues. And because they're all trues, so since the result is all trues, the argument is valid. Okay. Anybody got any questions about any of that stuff? Yes. Yeah, the conditional, which is this is a conditional and this is a conditional. And that's only true if it's only false if the first one is true and the second one is false. So you can see in this case we have a true on the left-hand side and a false on the right-hand side. So that was the only one that ended up being false. No, because you've got false. Yeah. So you're comparing this column versus that column.